Hi, welcome back. This is kind of an interesting topic, and that is resonance structures. And so if we take a look at something like ozone, ozone has a Lewis structure that looks something like so. And I'm not going to go through how to write the Lewis structure, I'm just simply going to write it out. And one of the things we know, right, is that double bonds should be shorter and single bonds should be longer, right? So double bonds are short and strong, single bonds are long and weak. And we go ahead and we do a lab, and in the lab experimentally we find that both bonds are identical. So the question is, right, how is this possible, right? Our Lewis structure, right, is predicting one bond should be longer and one bond should be shorter. But in actual fact, when we drew our Lewis structure, there was actually an alternate Lewis structure we could have done, and that is one where the single bond was on the left instead of the double bond, and the double bond was on the right. And we can go ahead and we can write it out and look something like so. And we might say, well, this is kind of interesting because in this Lewis structure, this should be short, this should be long. And this one, this should be long, and this one should be short. And what we want is both of them to be identical. So what we do, normally what we do to handle this is we write what we call a resonance hybrid arrow. So this is a resonance arrow, and it basically means that the true structure is a blend of these two. So the true structure is actually sort of a blend. You can imagine them being hybridized. And so that's actually a really good word here. So it's really a hybrid structure of these two. So what do I mean by that? I mean by that if you look in these structures, there's always at least one bond between the center oxygen and the outer oxygens. But in the left-hand structure, it's a double bond and a single. In the right-hand one, it's a single and a double. So if you like, each bond here is half the time a single, half the bond a double, or half the time a double. So I can write kind of a little dot here. And this is going to indicate that it's essentially 1.5 bonds. So I'm not quite sure how you would name that, but somewhere between a single and a double bond. And that, in fact, agrees with experiments. And so whenever we are faced with this situation, and quite often when you write the Lewis structure and you're like flipping a coin to decide which side gets the double bond, it often is actually really a blend of all those structures that are possible. Let me give you one more example. So for instance, if we look at the nitrate ion, experimentally, all the NO bonds are the same, both in terms of strength and length. And if we write the Lewis structure, what we'll see is that our prediction is in actual fact not the case. And so in our Lewis structure, we will see that we will have a double bond on one and two single bonds on the other. So it looks something like that. But in reality, right, where we made the double bond was kind of a choice. We could have picked there or there or there. So we can actually write another structure with a double bond to the left, and it looks something like so. A lot of dots here. Gotta love the dots, right? And then we can write another structure. Oh, I didn't give myself enough horizontal room, where we make the double bond off to the right. And so these are three different what we call resonance hybrids. So it is sort of 33% of the time this one, 33% of the time this one, 33% of the time that one, and 1/3. And so reality, it's kind of a blend of them. So the real structure, right, is a hybrid of these three. And so we can kind of draw a structure that looks something like that. And if we look at the bonds, what do we see? So it's double, single, single. So out of three structures, you've got 4 bonds. So if you like, it's 1 1/3 of a bond, okay, between each one of these 3 bonds. And so the true structure kind of looks something like that. And then experimentally, right, all the NO bonds were exactly the same. So that makes sense, right? So if it truly is a blend of these 3 structures here, we can see that it would give rise to 1.33 bonds between each one of the N's and the O's. And if all the bonds are the same length and strength, then that makes total sense.